Hello there. Welcome to a useful practical session on magnets. You probably read somewhere magnetic hysteresis loop. So what happens is when you try to take a magnetizable material and you try to make a magnet out of it. So you could do like here is a magnet, and then maybe you have a wires, and you try to pass a current, and so if the current is going this way, my current is going this way, you pass a current I, and then you will find that in here, so this is a magnetizable material, as for example ferromagnet, can be iron, and can be some alloy, as for example alinco. I think it's called alinco. I'm not sure this alloy that's actually is makes a good strong magnet. Okay, so when you pass it, this becomes magnetic. So what happens is you get an H field, and you also might get a B field, and might get an H field. And over here, they're in the same direction. And then if you reverse the direction of the current, so current was going this way, say you want to start the current that way, so maybe later on you switch the current, the H switches, but B may not switch yet, okay? Because B is mu naught H plus magnetization. So just because H switched doesn't mean, because this M may still be in the same direction, B will be in different direction. So you could say I want to plot, you can say 1 over mu naught B minus M. You can plot versus H, okay? You can plot B versus H. H is what you're applying, trying to make it magnetic, and you can apply, or you can plot M versus H. So sometimes you plot M versus H, sometimes B versus H, but B versus H is what I'm going to do in this, because that's directly related to what's accessible to experiment, and we'll talk about it in just a minute. So another thing to notice is that gets kind of not clear in the presentation in many places. If there's a direction to it, so Z, so we're talking about all the Z components. So we're going to think of Z axis, some axis along which both of these, at some point when I'm doing experiment, I just pick the Z axis and these components, and sometimes this is just written at B k hat, and this is just written H k hat. And so instead of this, you just write H, and instead of this, you just write B. So although we're writing a component here, drawing a component, we just, because there's only one component, we tend to not write the subscript. Okay, having said that, suppose you start with no magnetization and nothing, okay, so just plain iron bar or something, and you turn on the current, then the magnetic B and H will move on this kind of curve, and then at this point there is no more magnetism to have. So after there's B, you can see if I reach the maximum of that, so if just look at component wise, which is B equals to mu naught H plus mu naught M. So it's like a equation of a straight line in this plane, right? So this is now say some constant, then B equals to mu naught H, let's call it little b. So the H versus B will simply be proportional to H. The more H, the more B, and this will be the slope. And I'm not given the units and things like that here right now. So this can be like hundreds of thousands of amp per meter, and this could be a Tesla. This will be like a Tesla, and this will be amp per meter. Okay, and then if I switch the direction of the current, it doesn't come back to the original direction it went on. It actually goes to point C where the current is actually 0, and yet the B is not 0, and it continues, and then current is maximum, but the B is 0. So this is B equal to 0 line, and this is H equal to 0 line, and I continue in the negative direction the H, which will be given by the opposite direction current. So this will be opposite direction current. So current is either that way or that way in this experiment, and I reach this, and after that it just is going to be, again, this becomes M becomes maximum negative, and then at that point onward is just again the formula like that. So it's both B and H, all of these are negative, so again minus B minus mu naught H minus B. So this is exact back to the same equation again, and then if still H is negative, but now I'm making less and less in value, and H equal to 0, the B is doesn't have to be symmetric, but often is, and then it goes to G and then back to the original saturation, and then if I keep going, so you can, so this loop, this B, C, D, E, F, G, B, this is called hysteresis loop. So today we're gonna define a whole bunch of terms and talk about an experiment from which you generate this. This is one of the experiments you can generate this, but you have to know how to get B. We'll know H from knowing I, but then how do I get B? Because we don't know mu and things like that. So it's like a chicken and egg. If I knew mu, I could get a B, but I don't know mu, so how do I get a B? So you have to get a B from a different way. So we're going to talk about experiment. We're going to a little bit talk about hard and soft magnets. We'll also discuss the energy to go around this loop. And then if time permits, I'm going to do a numerical problem and designing a magnet in the lab. How do I, suppose for an experiment, I need to have some magnetic field in a small space. How to best get that design? Okay. All right. So this hysteresis loop. So we are on 1, and then A to B is magnetization. You can see B and C to D up to C is B is not 0, but B was not 0, H was 0. So C to D is the opposite, and that's called demagnetization. Okay, point B is called saturation. So see, this is Z direction, and this is the magnet. All the magnetic domains are kind of lined up in that direction. And E is saturation, and this is the magnet, this magnetic vector. Saturation, opposite direction. So at the E, same magnet, now domain all be down. So when you have a magnet has domains in which magnetization is pointed in the same direction. Large number of atoms, their magnetization is same direction, and so together they become a large magnetization. In a non-magnetic material, those atomic magnets, their magnetization is pointed in a random direction, and overall they cancel out, and that's why you don't have magnetization in the non-magnetic material. Okay, that you probably know from some place else. Okay, so their name for, you have a C and F, kind of similar situation but the opposite direction. So this is so it somehow is going to retain somewhere, so it's called retentivity. And sometimes it's also called remanence or remanence. Just a word for that, because there's, what we have here is H is 0, but B is not 0. That's the point. And if you look at D and G, kind of similar thing, D and G, this is called coercivity. There's a B is 0, and so this is B is 0, but H is not 0. So you have a H at point D and H at point Z. Now these are called coercive forces. So somehow H is preventing magnetization, is overcoming, the effect of magnetization. So what's happening here, if you look at this, B is 0, that means H is completely cancelling out internal magnetization of the magnet. That's why B is 0. So it's not like magnetization is 0. So at that point, you can say magnetization is equal to minus H. So at this point, magnetization at D equals to H at D, and magnetization G equals to minus H of G. So there is magnetization, but it is being coerced so that magnetic field is 0 inside the magnet. Okay, so so we covered B and E, and so yeah, so these are the terms that go with it. Okay, you can let's go with this next. The way you design hard and soft magnets is based on what are the values here. So saturation, we're talking about what the high B value, right? Or M, max M is a saturation. Saturation means max M and max negative M. Okay, so the hard magnets, if you look at the BH curve for the hard and soft magnets, for the soft magnet, this curves very easily. So it is. So this is very narrow, and so this is soft. For the hard one, is so this is the hard magnet, and this is soft. So you can say that maybe both can be very high saturation. So if you look at hard and soft, what are the differences? Both are high saturation. So let's see. So, but this guy has a small retentivity and a small coercivity. So both are small retentivity and large retentivity, is small coercivity, and but large coercivity. Both are used. The hard one, you can see, is harder to demagnetize and things like that, and harder to magnetize. What are the example materials for that? Let me look it up and I'll just write it here. Okay, so some of the example of so this is aluminum, nickel, cobalt. So this is an alloy, and steel. This is, for example, hard magnets, and the application is like a speakers. You can you probably look at the acoustic speakers, and you see there's a speaker. There's a magnet there. That's usually made of this, and soft one is soft iron, and they're used in transformers and other places. Okay. All right, so we covered this and this, and next I want to cover how do you get this plot. How do you get this plot in an actual lab? Over here it looks like you can do a lab, but how do I get a B? You can't get a B here, so you got to think of another way of doing it. And there are a couple of ways. I'm just going to cover one that I find very interesting, and can look at the way you can end up plotting the two if you set it up the experiment. Okay, so how do we get that hysteresis loop in lab? So here is a material, and it's done in a kind of ring, and with a cross-section area of the material is A, and overall radius of this is R. Okay, so we'll just do it a little bit approximately. I'll show you. Of course, you have to do a little more completely, but in principle you should be able to understand this, that if this current is I1, then if I take a loop, so if I solve this, H dot dl equals to I free or flowing enclosed plus d dt of phi of the D field, right? This D field is related with the electric field and polarization like that. Okay, but because we don't have electric phenomena here, we can just ignore that. So we just have this, and here the H, this direction we go is the phi hat direction. So I'll pick up this field will be this will be in the just phi hat direction, that will make h phi 2 pi, which is same as h phi hat, because this the entire thing, there's nothing more based on our observation here. So 2 pi r equals to, what's the current that's going to go through this, cutting this area? Well, each one of those n1 wires will current I1, so this will be n1 times I1. So writing this as h, so we got the h is n1 over 2 pi r I1. So or you can say 1 over 2 pi r n1 h1 n1 I1. So just by knowing this, from this you can have a in here you can have an ammeter. You go to the ammeter, so ammeter 1 and this ammeter 2. So there's a reading here. Now it's creating B. So how do I get a B? Well, we have a induced EMF, right? So we use to use induced EMF. What we have to do is not have I1 constant, but if I change this current, then it will, another current will be induced here through induction effect. And so if I look at the phi b that's going in here, this has to change. So phi b is equal to say the magnetic field is B and the area of cross section is A. So actually this is in the same direction, so the B is B phi hat, and the normal direction is also phi hat. So we assume that this is constant and uniform, so we just, for sake of simplicity, so this we just write at B phi hat, just like we did over there. So you can see that d phi b dt, A is not changing. It's A dB dt. But this will create a current in here. So this will create an EMF in circuit 2, and that will create a whatever the impedance of the circuit 2 is times current in 2. It may not be even phase, and we can there may be a little bit out of phase, things like that, but we're going to ignore all the little detailed complications. If you don't like it, you can just call it resistance in the 2, I2. And this B is the B in here, which was induced by changing current I1. If this is the case, so this B, whatever the B is, so you know, this is H, and it has some B associated with it. So if I change, so B will also be proportional to I1, but if I change I1, I can change B. Okay. All right. So so the I1, will just say I1 is a function of time at some time. So this is, I'm changing t. So B is a function of time. So this is okay. So this will create, and so I can say that dB dt is R2 over A, and then I2. So how much N2 I2? I'll just put it I2 here. The N2 will be inside the resistance, you know. So how much current I produce in the second circuit, and so if I want to get a B, this will be a function of time. R2 will be not function of time, and I2t dt. So if I integrate from 0 time to t time, so B at time t that goes with the H at time t will actually be obtained by integrating this current that you're reading. So R2 over A, integrate 0 to t I2t dt. Hence you get a B and you get an H at that time. So if you want to get to a particular H, so suppose I want to do an experiment where it's H and this side is B, and I want to know what the B will be for that H. Well, when there is 0, and so I go this, and I'm over here just before that H. So where is going to be that point? So this is where the sample is. So I've gone over here, and so to get this point, I just slowly, because I was here in the current, I go to that current. So this was and then I integrate how much more charges went to get the B, and that's going to be that B. And so all of these things are known. This is known, and all the multiplied things are known, and so you can actually plot this as you go around the loop. Okay, so that's a pretty interesting experiment to set up and do. Okay, so how do we get, usually this thing is left out of the textbooks, and I think there are some junior and senior textbooks that do address this, and mostly it's addressed in the engineering textbooks, and the physics textbooks do kind of gloss over this, and it's not good to gloss over because you got to do this experiment in physics, not just do theory, right? Another question is when I'm if I am at the point B in there, and then I come down like this, C, D, E, F, G, and back to B. Okay, so how much energy is going to take to go through this loop? And that's the topic 4, and let's clean this up and see how we can do that. Okay, so we're gonna do the energy around, if I go around the loop. So we are here and we go like this, and so this is B and this is H, and start with B. We are going to go this way. We can go any which way, just maybe start with G, and then you have B equal to 0, and then some magnetization, and then you go to B, and then all the way. Okay, so how do we do it? Well, so what will happen when you change say this current? When we change I1, we are going to have to work against self-induced back EMF, right? So we have to work against changing I1 with T will means back EMF. So if that would mean I will have to work against the back EMF, and the back EMF will be d phi b dt. Okay. And you have a current I1 and this n loops, so the phi b is phi b per loop. Phi b is b times a, just one loop. Then I need to multiply by n1. There's n1 loops, so this whole thing. And if I so this is the EMF, back EMF, and then the current is I1. It's trying to push through the back EMF, so I times V, right? And that will be the rate at which I have to put this is the rate at which energy energy has to be supplied, energy supplied to this circuit. Okay, so it seems like I should be able to cancel dt on both sides and make some progress here, right? And that's actually true. I can make some progress. One more thing I can do is I can write this in terms of h. So this will be first dt cancel out both sides. So amount of work, it's a tiny amount of work for tiny amount of time, is it's going to be h time 2 pi r, which is some constant, times h times this is the length of this. Let's call it the length of this whole thing. Okay, and then you got h, and then you have a d phi. There's going to be area of cross section, which is this area, times whatever the b dB. So now A and L is that volume, the space inside, times h dB. So here is a B as a function of h. I can think of h as a function of B here. So this can be thought of as B lambda. Here to here is, is for same h there are two B's, and for the same B there are two h. So it's like a double valued function. So you can be h lambda, and you can parameterize the lambda 0 to less, and then you can say, okay, with this curve you can go all the way around, kind of like a circle. How do you parameterize? You get a x and y. X equal to cosine theta and y is equal to sine theta, and if the radius is a, then you just parameterize with theta, right? So this, you say x with theta and y, and if you just wanted to have a 0 to 1, then say 2 pi theta and 2 pi theta. So and to 0, theta will be 0 less than 1. So you go entire circle. So that's the parameterization you do there. You can do a similar parameterization for this, because this is experimentally determined now. So you have access to this and trying to figure out how much energy it took. Okay, so you can see I can go around and do this integral. Volume is outside, h dB in the loop. I go around the loop. So this should be the answer. What is this answer? Well, this stuff is the area that's in there in that loop. So this is like a volume times the area of the hysteresis loop. Okay, that's pretty good. So that's how you can compute the energy that you need to actually do this experiment, and you go around the loop. Okay, let's do an application of these ideas. So one of the application is that you remember we did an example. So we had a magnet here and a magnet here. Usually you taper it a little bit, and you go around. So this is some kind of core, and this is a magnet, and this is a magnet. Let's say these are identical magnets, and there is some kind of gap here, say air gap, and this is where you are going to do an experiment. This is the space you're going to bring a sample. So this is the space you want to set up some kind of magnetic field. You're going to do experiment on a sample. Okay, and the question is what kind of magnet you need. So you know how much space you need, right, for your experiment over here, how much air gap you need, and so how much magnet this magnetic material, so like what's the volume of this material, what's this area of cross section you need. So area of cross section of magnet, and what's the length of the magnet you need. Let's say this is also length, okay, and maybe it's the same area of cross section. So we're going to do an numerical problem to find out these guys, given the requirement, say require you are going to, in the gap you need require some level of magnetic field you need, and you need to work with some height here, let's go length of the gap, and you want to know some area of cross section of the gap. So this is your requirement. How do you decide what kind of magnet you need given the hysteresis loop of the material? So this hysteresis loop will vary from material to material. Okay. Okay, so this is actually a good, interesting numerical problem that we can practice on and learn some of the concepts. So we have a setup with a gap. There's the air gap, and there's a magnet here, and there's a magnet here. Okay, so you might say this is magnet 1 and magnet 2, and this stuff between here to here is air gap. Okay, so some of the properties are given. So we are supposed to get a magnetic field here, which is 2 Tesla, which is pretty strong magnetic field, and we could use electromagnet to get that, but we're going to use just a permanent magnet, and favorite material is alnico 5 alloy. And when you do the hysteresis loop for that material, you have this as a result. Okay. Now, I mean, you could do experiment at any of these results where you can freeze this H and B. So here is where do you freeze it? If you freeze it here, then the values are this and this, but those values, the product H times B is maximum, Okay, HB is maximum. If you say what's the HB for that, what's the HB for that, HB for that, so they're not as big as this. So H times big B is the maximum for that point. Okay, we'll see why that is important. So it turns out the magnetic energy in the gap, so like a magnetic energy in the gap is 1/2 mu naught the volume of the gap times magnetic field in the gap squared. So you know from before, magnetic energy density, this is magnetic energy density and multiply by the volume. So now you can actually carry out the calculation, and this will become this will become like this plus this length of the magnet, and area of the magnet is the same, both of these. So area of the magnet, so this calculation I will show you just a minute, but this calculation, the result is H of the magnet and B of the magnet. I don't want you to get in the results this step. To appreciate that, usually this is the volume of the magnet. This is like so much material you need. Okay, now you want to minimize that, you don't want to maximize that, but you definitely want to maximize the energy, magnetic energy that's in this stuff, so that you can act when you do the experiment. You're doing the experiment with a maximum efficiency of your experiment. Okay, so you want to maximize this. So you want to pick a point where this is maximum. This one you want to minimize, because more you have it, more material, more heavy it is, difficult to handle, and weight and the cost goes up. So that's why maximize it. Just to show how you might be able to get from here to there, let's do a little calculation. The volume is LM, AM, LG, AG, and you have a BG times BG. So you can LG with 1 BG, and with 1 BG you can so 1 of the BG with LG, BG over mu naught, and you have a AG, BG. So this goes with the flux, and flux being the same, so this will just become AM, BM. So same flux, no loss. I know there will be loss here, so no, we say no leak of flux. So usually, you lose 50%, 40%, 70%, you lose big, but we can assume no leak, okay, for the purpose of calculation. And so this just becomes Hg, and if you go around a loop, a calculation like that, so you have a Li Hi plus Lg Hz minus in here and in here, that makes it Lm over 2 Hm plus Lm over 2 Hm equal to 0. So this will just give you Lg Hg. So Li Hi is much less than Lg Hg. That just means this gives me Lg Hg equals to Lm approximately Hm. So this is half Lm M, and this thing just Am. Okay, so this Lm Hm and Am Bm, and this gives me that. Okay, let me erase this and because it's kind of tangential thing, and do this problem. So to do this problem, we do need a this L loop. So this H dot dl equals to if enclosed plus d dt phi d. So this is 0, this is 0, this is both are 0, so this is equal to 0 here. Go around the loop, and this just gives me h in the I, L of I, plus they're in the same direction going, h of the gap, L of the gap, minus this and this gonna be negative, hm lm equal to 0. And so this is way smaller than that, so we can just ignore that. And so I should be able to get I want h m lm equals hg lg, and I want lm, so this is going to be on the other side, so lm just going to be hg lg over hm. Now we are using hm at star, and hg is 2 Tesla, so the over mu naught, so 1 over mu naught bg lg over hm star, and numerically we can just work it out. And so bg is 2 Tesla, lg is 1 centimeter. Don't need to change units there because this will cancel that. So 4 pi times 10 to the minus 7 for mu naught, and hm star is, I'm going to use a plus value, absolute value, because we already took the direction into account. 3.6 times 10 to the power 4. So let me see what. So I found this pretty large magnet. So basically 20 centimeter here, roughly 20.4 centimeter, and this one is 20.4 centimeters. How thick thickness will be in the area of cross section. So to get the area of cross section, we're going to do the flux in the gap equal to flux in the M, and so this side is AM BM, and this side is A gap B gap. So BM already is at BM star, so AM just gonna be BG over BM. I'm at BM star, and AG. So BG is 2 Tesla and BM star is 0.8 Tesla, and this can remain in centimeter square. These units will cancel out. So this is actually whopping I think 50 centimeters square. So that's like a 7 centimeter by 7 centimeter approximately. If you had a square, so this is pretty thick, and it's going to weigh quite a bit. All right, so these are large magnets in this example. Okay, so you can see the applications are somewhat not that difficult to do, but to get to that, all this extra stuff, it takes a while to learn it. Maybe you want to watch this video a couple of times. You can speed up and watch a couple of times. If you miss something, let me know. If you need some clarification on any of these things. If you like this kind of explanation, you can hit the like button, and if you haven't subscribed to this channel, you subscribe, then it gets distributed to a lot more students, and other professionals. Okay, so much for now. Take care. Bye.